Welcome to Mana TV classes. Today's topic is on graph theory, which has been offered as a cluster paper for 3rd B.Sc mathematics students in most of the universities and autonomous colleges. So, I am very happy to teach a class on this topic. So, my dear students, so today's class I am very happy to dedicate this class to Professor G. Ravindra, our professor at Regional Institute of Education, Mysore, who introduced me to this subject called graph theory. So, in 97 itself. So, I am in a way very happy to teach this topic, a lesson on this topic which I learned somewhere in degree courses. So, this lesson involves 3 subtopics. So, the first one is the motivation, and the second one is basic concepts, so which involves definitions and certain simple results, and the third part is more information about graphs. So, without making any delay, let us get into the motivation. So, what I believe is for most of the discoveries and inventions, it is a necessity which leads to the inventions and discoveries. So, in case of graph theory also the same is true, same happen to be true. And it is known that in the literature that graph theory was discovered by many people for many times, involving mathematicians and non-mathematicians. So, let us know about a discovery that was made by a mathematician called Euler. So, as we know, the Leonardo Euler, a famous original mathematician who lived in the span of 1707 to 1782. So, he is already a father of topology and mathematical analysis. He is known to be the father of graph theory also. So, the situation that led to the discovery of graph theory is as follows. So, this problem is called Königsberg bridge problem. Königsberg bridge problem. So, before going to this problem, let me say a few words about Euler. Euler is a Swedish mathematician. Basically, he made so many contributions in the branches of mathematics like analysis, mathematical analysis, fluid dynamics, classical mechanics, and many so differential equations and what not. So, he is known to be the legend in the various fields of mathematics. Now, when it comes to the graph theory, especially the Königsberg bridge problem, so this problem motivated Euler to discover graph theory. So, let us know what is this problem actually. So, as shown in the figure, if you understand, the Königsberg is a name of an area now presently situated in Russia. So, there was a folklore in that area involving a puzzle. So, what was that puzzle is, so you can see the area of Königsberg. This is an island, the collection of islands like A, B, C, D. So, there are 4 land areas in this Königsberg, which are connected by 7 bridges. You can see the numbers 1, 2, 3, 4, 5, 6, 7. So, Königsberg is a collection of islands, 4 land areas A, B, C, D, that are connected by 7 bridges 1, 2, 3, 4, 5, 6, 7. Now, the folklore which involves the puzzle is as follows. So, begin at any 4 of the land areas and walk across each bridge exactly for once and return to the starting point. So, let me repeat the puzzle. So, begin at any of the land area, either A, B, C, D. Suppose you start from A and walk across each of the 7 bridges only for once and return to the land area A. So, the question is it possible? So, this was a puzzle which was very famous in the area of Königsberg as a folklore. And many people, they were thinking about that and they could not solve. So, it happened centuries, years and years. Somehow it came to the European mathematician Euler, Swedish mathematician Euler. So, Euler thought about this and he thought how to solve this. Actually, he thought whether it is possible. Then he thought how to prove that it is possible or not possible. So, for this purpose, he simplified this problem in the form of a diagram which he called as a graph, So what he did was he replaced the places, the land areas that are A, B, C, D by points. You can see in the diagram, and the bridges which are connecting the land areas by lines connecting A, B, C, D's. So from the Königsberg figure we can draw this graph. So where the points denote the land areas and the joints, the lines denote the bridges, the 7 bridges that you can see. So C is connected to D by 1 bridge, C is connected to A by 2 bridges, A is connected to B by 2 bridges, and A is connected to D by single bridge. Like that he prepared a graph of this type. Then he started studying this, whether it is possible to travel from single point, starting point, and traveling each line for only once, exactly once, and coming to the starting point. So he thought and he analyzed the picture completely, and if he went into the depth of the graph theory, he himself framed a general rule also, general principle also, which is called Euler's principle, which states that it is not possible. So by that Euler solved the famous unsolved problem of that time, which was Königsberg 7 bridge problem. So this was the motivation behind the discovery of graph theory by Euler. So let us come to the basic things. So what he did was he called these points as vertices and the lines as edges. So even though the nomenclature vertex edge is there, but we simply refer to them as points and lines. And another notations, another nomenclature is there, points are referred as nodes and lines are referred as edges. So different books follow different nomenclature, but if you understand points, lines, or any other nomenclature like vertices, edges, so is it clear to everybody? So what Euler did, he replaced the land areas by points and bridges by the lines joining them. So the picture which he obtained, he called it as a graph. So in that graph the points are called vertices and lines or bridges are called edges. So this was the motivation behind the discovery of graph. So Euler successfully he could solve the problem. Later on he also developed so many concepts in graph theory, and there is a formula called Euler's formula, which is for what we call regular polyhedras, which involves a formula about vertices, edges and faces of a regular polyhedra. So I hope the students got enough motivation behind graph theory. It is not only that, even the book which I referred for graph theory, he talks about Archimedes, who is also a famous philosopher, Greek philosopher, and he also invented so many things, but everything had a necessity behind it. So for example, he invented buoyancy law, the law of buoyancy. So what was the motivation behind that situation? So it was his king gave a crown to him to see whether it is a genuine, it was made by genuine gold. So for that he thought when he was in a bathtub, he suddenly got an idea and he ran to the king and he said, "Eureka, eureka." So as I feel that any branch of any discipline is out of necessity. So I hope students understood this, the motivation behind graph theory. So let us pass on to the next topic, that is basics of graph theory. Basics of graph theory. So let us start basic concepts of graph theory. So we already made an informal definition of graph using the Königsberg bridge problem. Now let us give an exact definition what is a graph. So this part, second part of this lesson consists of series of definitions, so which students have to know certainly. So a graph G consists of a finite non-empty set V of points. So we denote that number by p, small p, together with a prescribed set X of q edges, q unordered pairs of distinct points of V. So, let me read once again. So, graph is nothing but a finite non-empty set of points. How many points are there? P points together with a prescribed set called X. So, which consists of unordered pairs of distinct points, unordered pairs of distinct points of V. So, here the set V consists of vertices or points of the graph, and X consists of edges or lines of the graph. So, that lines were representing by unordered pairs of distinct points of V. So, we are completely transforming the terminology into set theory. Okay. Is it clear? So, graph G should have a set V of P points and a set X of Q unordered pairs of distinct points of V. So, as shown in the figure, you can see the graph has 6 points A, B, C, D, E, F, and the lines are there, the connecting lines are there. So, you can see these the V forms A, B, C, D, E, F, G, E, F, 6 points, and the set capital X consists of these lines joining AB, AC, AF and BC, BC, CD, CE, DE, EF. So, as he is saying unordered pairs of distinct points, you can see no loops are allowed, because distinct points should be there, each pair should cut in different points, no loop is allowed, and at the same time we are taking unordered pairs. So, no multiple lines are allowed between any 2 points. So, is the definition clear? Okay. So, in the set formality we have given the definition. So, now let us understand. So, if you write say X is equal to UV, this means X is a line joining the vertex U and V in the graph G. X is said to join the vertices U and V in the graph, and again it is also written X is equal to UV simply. So, to say that U and V are adjacent points, U and V are adjacent points means they are joined by the line X, they are joined by the line X. So, if I show in the figure, so in a graph say this is U and this is V, this is the line X. So, let us go to the next concept, multigraph and pseudograph. So, as we defined in the definition of graph, no loops are allowed. Loops means a line joining a point to itself, that is not allowed, because we are specifically making that unordered pairs of distinct points. So, A comma A is not allowed, so no loop is allowed, and AB BA is not allowed, okay, because we are saying unordered pairs. Okay. So, no loops, no multiple lines are allowed. So, please understand. So, that is why we are defining another term called multigraph. Multigraph is a graph with no loops, but more than one line can join 2 points, that are called multiple lines. So, between any 2 points you can have more than one line. So, for example, in the Coinsberg bridge problem, that is what happens. Between A and C we have 2 lines, between D and A and B we have 2 lines. So, there are multiple lines, but there are no loops, you can see. So, that is what we call. So, a multigraph is nothing but a graph with no loops, but with multiple lines, right. So, if both loops and multiple lines are permitted, then that graph is called pseudograph. So, that is the picture which we are showing is a pseudograph, where you can see multiple lines are allowed and loops are also allowed. It is somewhat complicated graph. Okay. So, let us go to the next concept, that is a directed graph. So, directed graph, the name itself indicates that it is a it has directions. So, it is called, another name to this is a digraph. So, a digraph is nothing but set of points V together with a collection X of ordered pairs of distinct points. So, we are specifically saying ordered pairs. So, if I write A comma B, then we are drawing a line that represents a line from A to B, a directed line from A to B. Is it clear? So, that is why the elements of X are called directed lines. So, simply there we call lines or edges. So, here directed lines we call. And again the definition of digraph or directed graph clearly implies that it has no loops and no multiple lines, because we are saying ordered pairs of distinct points. So, distinct point means no loops are allowed, and already we are saying ordered pairs. So, no question of multiple lines. So, this also has applications in many parts of sciences where optimization is involved, right. So, let us go to the next concept, that is isomorphism of graphs. So, since we are defining the concept of graph in the form of sets, so automatically the mapping comes into the picture. So, even when we study group theory or rings, fields, once we define a ring, a structure, automatically we try to relate two such structures. So, here also same. So, we call two graphs G and H are isomorphic, and it is written usually G is equal and semicolon H. If there exists a bisection between two graphs, that bisection should be in such a way that they should preserve adjacency. They should preserve that bisection should preserve adjacency. So, my dear students, please remember that in case of isomorphism of two groups, of isomorphism of two vector spaces, we specify this. They should preserve binary operation. So, here also that isomorphism or that bisection should preserve adjacency. So, let me show this with an example. So, suppose I am having a graph with 5 points, say. So, this is a regular pentagon. So, this is V1, V2, V3, V4, V5. So, I can draw a graph, say this is G. So, we can draw a graph which is isomorphic to this. So, that is I am calling it as H, so which is a star graph. So, call this is V1, V2, V3, V4, V5, or I can say U1, not exactly V's. So, I can use some other letters. So, this is U1, say U2, U3, U4, U5. So, do you see the preservation of adjacency? So, suppose I map Vi to, my bisection is Vi to Ui. That is, so if there is a line joining V1 and V2, so certainly there should be a line between U1 and U2. You see? So, if there is a line between V3 and V4, certainly there should be a line between U3 and U4. So, this is what we call, that should happen for all vertices present in G and also in H. So, in that case that bisection is called an isomorphism between these two graphs. So, a given graph, if it has isomorphic graphs, can be written in different ways as shown in the figure. So, is it clear? So, let us go to the next concept, which is substructure. So, we always, whenever we define group, we immediately define subgroup. Whenever we define vector space, we say subspace. So, substructures are always possible. So, again subgraph, so we are saying subgraph is nothing but it is a part of graph. So, subgraph of a graph G is a graph having all its points and lines from G. So, it should come from original the graph G. So, as shown in the figure, you can see G is the graph shown on the right side, its subgraph S is shown on the left side. So, simple a square graph you can see just a part of G. So, the points in the S are points in G, the lines in S are also lines in G. So, it is the same concept which we do in any group theory or algebraic structures. So, this is the concept of subgraph. So, let us go to the next very important concept of graph theory, that are walks and connectedness. Walks and connectedness. So, what is a walk? So, a walk, once we are given a graph G, so a walk is nothing but an alternating sequence of points and lines, points and lines. So, we are writing like this. So, V0 is a point and followed by the line x1, next followed by the point V1, next followed by line x2 and so on Vn minus 1 xn Vn. So, please understand the walk is nothing but an alternating sequence of points and lines V0 x1, V1 x2 etc. Vn minus 1 xn Vn. So, what is the nature of this sequence? It is beginning and ending with points. beginning and ending with points, and in which each line is incident with 2 points, which is preceding and following. So, suppose x1 if you see, it is incident with vertex v0 and also with v1. x2 if you see, it is incident on v1 and v2. Incident is nothing but joining. So, the sequence has to have this nature. So, such sequence is called a walk joining points v0 and vn, v0 and vn. So, suppose let me show in this example. Suppose this is my graph. So, suppose h is the graph I am showing. So, u1, say this is x1, x2. So, I can write the sequence as u1, x1, u2, x2, u3. So, this is a walk joining u1 and u3, having lines x1 and x2. Is it clear? This is called walk in a graph. So, you can start from any point and take the help of lines and pass it to another point. That sequence is called a walk. So, this walk is called closed walk if starting and ending points are same. So, do you understand? So, if starting and ending points are same, that becomes a closed walk. So, suppose u3 I am coming, and next I will take the help of x3, u4, x4, u5 and say x5, u1. So, I am coming back to u1 once again. So, this form you can look at the picture u1 x1, u2 x2, u3 x3, u4 x4, u5 x5 and coming back to u1. So, this is called a closed walk, okay, where starting and end points are same. Otherwise, it is called open walk or simply walk. Is it clear? These are all terminologies which have to be remembered. So, it is called a trial if all the lines in this walk are distinct. If all the lines in this walk are distinct. So, it is called a path if all the points are distinct. So, please understand. So, if all in a walk, if all lines are distinct, that walk is called a trial. If all points are distinct, that walk is called a path. Okay. So, if the walk is closed and all its points are distinct, then it is called a cycle. So, a closed walk with distinct points, that is all, is called a cycle. So, this is a cycle where we are using distinct points u1, u2, u3, u4, u5. So, it is a cycle. So, certainly for making a cycle in a graph, how many vertices should be there? Certainly n, that n has to be greater than or equal to 3. Is it very clear that to have a cycle in a graph, the number of vertices n has to be greater than or equal to 3. Is it clear? So, let us go to the next concept, Cn. So, we denote a graph by Cn as a graph consisting of a cycle with n points, and just now I said C3 is called a triangle. C3 is called a triangle, and similarly Pn is the notation used for a graph consisting of a path having n points, of a path with n points, of a path with n points. So, these are the concepts walk, closed walk, trial, path and cycle, and graphs, notations of graphs having these concepts Cn, Pn, etc. So, many 6 concepts totally we defined. Now, let us come to the connected graph. So, when do we call a graph is connected? So, a graph is said to be connected, మన కామన్ సెన్స్లోనే ఎప్పుడు కనెక్టెడ్ అని చెప్తాం, if every pair of points are joined by a path. We do not say line, it need not be a line, it should be joined by a path. So, in a graph if every 2 points are connected by a path, path means again a walk having distinct points, So, such a graph is called a connected graph. If this is not possible, then that graph is called disconnected graph. Suppose I have 2 points in a graph which are not joined by any path. So, any path does not join these 2 points then such a graph is called disconnected graph. So, you can see in that case the graph can be divided into two parts, so which are called components. So, a disconnected graph can be made into components. Okay. So, next another concept is degree of a vertex, degree of a vertex in a graph. So, is it clear? So, totally we had defined what is a walk, closed walk, trial, path and cycle, and to have a cycle minimum number of points required is 3, and Cn is the notation used for a graph having a cycle of n points, and Pn is the notation used for a graph consisting of a path with n points and connected graphs. So, so many concepts we defined which are very simple concepts, not at all difficult. So, if you go through the examples everything will be clear. Now, let us come to the very important concept that is called degree of a vertex in a graph. So, in a given graph G, so degree of a point Vi is nothing but number of lines passing through the vertex Vi. So, in other words it is defined as number of lines which are incident with Vi, and it is denoted by di or degree of Vi, di or deg Vi. For example, in this graph itself you can say what is degree of V1? V1 means how many lines are passing through V1, it is 1, 2. So, degree of V1 is clearly 1, 2, and degree of V5 again 2, 2 lines are passing through V5. So, degree of V5 is also 2. Do you understand? Similarly, what about degree of U1? How many lines are passing through U1, or in other words how many lines are incident on U1. So, 1, 2, only 2 like that. So, as I included an example of Koenigsberg bridge problem. So, if you go back to that graph, so what are the degrees of the vertices A, B, C, D? So, you can see how many lines are passing through A. So, above 2, below 2 and horizontally 1. So, totally 5. So, degree of A is 5, and degree of B is above 2 lines and other side one more slant line. So, the totally 3. Degree of C same 3, degree of D 3. So, in any graph we can talk about degree of a vertex. So, based upon this degree of vertex only Euler could solve the problem of Koenigsberg bridge problem. That is a theorem, okay. So, which we are not dealing in this class, and that can be dealt later. So, is it clear what is the degree of a vertex in a graph? So, having done so many concepts, definitions, what I would like to do is what are the nature of results in graph theory? What are the nature of results in graph theory? So, certainly the results will not be in the usual way of where we study in linear algebra or group theory or differential equations, but these proofs involve combinatorial theory like counting formula, nothing but counting formula. So, just I want to show the glimpse of certain results, which is called the one which we are exhibiting is handshaking lemma. This is called handshaking lemma, which goes like this. The sum of the degrees of the points of a graph G is twice the number of lines. So, it is a very simple statement known as handshaking lemma. Sum of the in a graph G, sum of the degrees of all the points is equal to twice the number of lines. So, in symbols if you write, it is sigma degree of Vi, where V belongs to the set of vertices capital V should be equal to 2 times Q, where Q indicates number of lines, number of edges in the graph G. Is the statement clear? So, what is the proof? So, take any graph or imagine any graph and think about a line. So, a line is counted twice, because always, for example, you look at this graph, a line this say if I call this line is x joining V1 and V2. Suppose I want to count all the edges, all the lines in this graph G. So, this x is counted while calculating degree of V1, and also while calculating degree of V2. Is it clear what am I saying? So, any line in a graph is counted twice. Eppudu while counting the degree of V1 and while counting the degree of V2. So, certainly when you add all the degrees of the vertices, certainly what happens? So, it should be certainly twice the number of lines in the graph G. So, that is what the statement. So, a very simple statement, a simple result is given as handshaking lem. So, in a graph G, every line contributes twice to the degree of points. So, that is the lem. So, is the proof clear? Is a simple proof clear? So, a corollary, an immediate corollary to this handshaking lemma is nothing but in a graph the number of points of odd degree is even. The number of points having odd degree is even. So, what is the proof for this? So, again from the handshaking lemma, because it says sum of the degrees must be equal to twice the number of edges, twice the number of lines. Now, divide this sum of the degrees as sum of the odd degrees and sum of the even degrees, sum of the odd degrees and sum of the even degrees, that is so this is 2q is clear. Now, I am writing sum of odd degrees plus sum of even degrees. You can say this is an even number and this is an even number. This is an even number, this is a number, so this has to be even. So, sum of odd degrees has to be even. So, when will it be even? These are all odd numbers. Odd degrees means they are all odd numbers and that sum is going to be even. So, ఎప్పుడు జరుగుతుందండి? బేసి సంఖ్యల మొత్తం సరి సంఖ్య ఎప్పుడు అవుతుంది? Certainly ఎన్ని బేసి సంఖ్యలు యాడ్ చేయాలి? సరి సంఖ్యలో. So, the number of that odd numbers have to be even number. So, that is the corollary. In a graph, the number of points of odd degree is even. So, it is a type of counting. So, let us go to the another result. It is also very simple result. If G is a P comma Q graph, so you should understand this notation. Any graph is written P comma Q, means P vertices Q lines, P vertices Q lines. So, if G is a P comma Q graph with P vertices and Q edges, then Q is less than or equal to P into P minus 1 by 2. So, this theorem gives how many maximum number of lines a graph could have. ఒక గ్రాఫ్ లో గరిష్టంగా ఎన్ని లైన్స్ ఉండొచ్చు when I have P points. So, to count this, since we are talking about only a graph means no loops, no multiple lines. So, let us calculate degree of each vertex, degree of each vertex. So, degree of the first vertex ఎన్నింటికి జాయిన్ చేయొచ్చు నేను? రిమైనింగ్ P minus 1 vertices, అంటే P minus 1 లైన్స్ నేను P గుండా ఫస్ట్ వర్టెక్స్ గుండా పంపించవచ్చు. So, that is P minus 1. Next, degree of the second vertex is P minus 2. ఆ విధంగా degree of the third vertex is P minus 3, because you can say why not degree of the second vertex is P minus 1. Is it possible? No, because we are talking about only a graph where no loops, no cycles are permitted, no multiple lines are permitted. కాబట్టి అక్కడ P minus 1 వచ్చాయి కాబట్టి ఇక్కడ ఒకటి తగ్గాలి, ఇంకా ఆ ఎడ్జెస్ని ఆ పాయింట్కి నేను మళ్ళీ జాయిన్ చేయలేను. Is it clear? So, the second vertex has to have degree P minus 2, the third vertex will be of degree P minus 3 and so on. What is the degree of P minus 1th vertex? Is 1. అక్కడ ఏమీ ఉండదు, only it has to be joined by. So, now calculate total number of edges. So, degree is nothing but number of edges, distinct edges. So, calculate total number of edges, that is P minus 1, P minus 2 and so on 2 plus 1 by some of the natural numbers formula. It is P minus 1 into P minus 1 plus 1, which is P into P minus 1 by 2. So, this gives maximum number of edges in a graph can possess, but we are saying number of edges is Q. So, certainly the Q has to be less than or equal to P into P minus 1 by 2. Q has to be less than or equal to P into P minus 1 by 2. So, is it clear, my dear students? So, this is the nature of statements and proofs that we have to provide in while studying graph theory. Okay. So let us go to the another important concept of graph theory, that is called trees. So briefly I discuss a graph is said to be acyclic if it has no cycles. So we have already defined cycle, a closed walk, right, having distinct points. So if it has no cycles, that graph is called acyclic. So an acyclic connected graph is nothing but tree. So a tree is nothing but a connected acyclic graph, and a graph has to be connected, and in a graph every 2 points have to be connected by a path, but no cycle should be there. ఎక్కడ క్లోజ్డ్ పాత్స్ కనిపించకూడదు. సో నేను బొమ్మలో చూపించాను చూడండి, దట్ ఈస్ ఎ టిపికల్ ఎగ్జాంపుల్ ఆఫ్ ఏ ట్రీ. సో హ్యావింగ్ 1 2 3 4 5 6 వర్టిసెస్, మీరు చూడొచ్చు ఎక్కడ అన్ని పాయింట్స్ని కూడా జాయిన్ చేసాము, బట్ ఎక్కడ సైకిల్ రాదు చూడండి. యూ కెనాట్ హ్యావ్ ఎ క్లోజ్డ్ వాక్. సో దిస్ స్పెషల్ కేటగిరీ ఆఫ్ గ్రాఫ్స్ will play an important role, have been playing an important role in the graph theory, not only in mathematics, in other sciences like physics and chemistry also, which we will discuss now. So just let me state a theorem about trees. So first one is G is a tree, all these statements are equivalent. So you can try to prove this with simple definition only. G is a tree. The second one is every 2 points of G are joined by a unique path. Third one is G is connected and P equal to Q plus 1, and fourth one is G is acyclic and P equal to Q plus 1. Fifth one is G is acyclic, and if any 2 non-adjacent points of G are joined by a line x, then G plus x, a graph added line x, has exactly one cycle. So these are statements which are equivalent in case of trees. So we can also have simple proofs. నేను జస్ట్ ఒక ట్రెండ్ మీకు ఆ రుచి చూపిస్తాను చూడండి. సో 1 implies 2 quickly. So since G is a tree, it is connected acyclic. So కాబట్టి any 2 points have to be connected by it says unique path. Suppose there are 2 paths. Suppose there are 2 paths between vertices, say V1 V2. What happens? So you start from V1, choose the first path and reach V2. Now start from V2 and choose the second path and reach V1. So what happens? There will be a closed walk, a cycle will be formed. So kabatti G is said to be a tree, a connected acyclic graph. So no cycles are allowed, but we are getting a cycle. So no any 2 points are joined by a unique path. Next, 2 implies 3. It says G is connected and P equal to Q plus 1. And because every 2 points unique path are not, they are joined by a path, so it is connected. And now try to prove P equal to Q plus 1. So students yourself can derive these statements from simple definition. Okay. So by this I am closing the part 2, which is the basic concepts. So let us go to the third part, that is more about graphs. So let us know more about graphs. So the first part we learned about motivation, what is the inspiration, and second part we learned about some basic concepts of graph theory and some nature of simple results. Now let us understand some more information about graph theory. So even though the graphs, the motivation for discovery of graph theory was made by Euler, as I mentioned in the beginning of this class, it was also discovered by many people many times. So the Kirchhoff, the famous physicist, he developed the theory of trees in 1847, of course after Euler only. So he developed these tree diagrams to write down the electric networks, to write down electrical networks or circuits. So circuit ante emem untai, batteries, condensers, resistors, inductors and so on. So he tried to write these electric networks in the form of a graph, where the points are denoted by these electrical items, a battery, resistor, inductor and so on, a capacitor, and the lines joining them will give the connections which are shown in the electrical network. Suppose in the diagram shown, the resistor R1 is connected to R2. So, I also join a line connecting the point indicated by R1 to the point indicated by R2. So, this type of graphs, and as I said, he developed the theory of trees. Okay. So, what was the purpose for which Kirchhoff developed is to solve the system of simultaneous linear equations involving these resistors, current flow, voltage, inductance, capacitance in any branch of the circuit, and he developed a standard procedure also for this purpose using trees. So, in a way the special category of graphs which are called trees were discovered by Kirchhoff also. So, another branch, another science, that is chemistry, also involves graph theory in the form of chemical isomers. So, it was in 1857 the chemist Cayley, he started using trees, again the important class of graphs which are called trees, for enumerating isomers of saturated hydrocarbons CnH2n plus 2, CnH2n plus 2, where n is the number of carbon atoms. So, for a given n you can have a hydrocarbon. So, for example, if you take n equal to 1, you can have CH4, it is called methane. So, what are the isomers to write? So, he also developed again a procedure. So, primarily he decided that the degree of each point. So, here also tree, how did he write trees? Each point denotes the atom, it may be carbon atom or it may be hydrogen atom, oxygen atom, anything, and the lines indicate the bonds between them, So, for example, for methane CH4, if I write in the form of a tree diagram, he fixed that every point should have degree 4 R1, but that was not a successful procedure. Later he changed it to at most 4, again it was not possible. Later he fixed it, he fixed degree has to be either 1 or 4. So, by that he could develop so many isomers for given hydrocarbons. So, for example, this is one isomer. So, this is CH. So, when n is 2, so this is another hydrocarbon C2H6. So, like that he developed the theory of trees for enumerating number of isomers for hydrocarbons. And next one, very famous puzzle this is also, which is named as around the world. So, this game was invented by Sir William Hamilton in 1859, again after Euler. What was the puzzle is? There are 20 cities which were shown in this dodecahedron. It is a regular polyhedra having 20 vertices. So, the puzzle is here the person has to travel all the 20 cities using each edge, each line exactly once. So, prati city gunda prayanam cheyali okkasare, and again he has to reach the starting point. It is just like Königsberg bridge problem, but here the centers, the vertices are increased, and their situation, their location is also around the globe. So, that is why a 3D dodecahedron was used. So, this not only to just solve the puzzle, it also leads to the optimization problem. So, choose a path or a cycle or a closed walk which uses the minimum time and minimum expenses. So, there also the graph theory finds the application. And finally, I want to talk about the 4 color conjecture. 4 color conjecture. So, it is a famous still unsolved problem in graph theory. Not only in graph theory, the whole mathematics it is an unsolved, famous unsolved problem at present, which is called 4 color conjecture. So, please note that students, if a statement is given a valid proof, then it is called theorem. Until then it is called conjecture. So, we have so many conjecture in the literature of mathematics. So, what is this 4 color conjecture is, you take any map, a map a plane or a surface of a sphere and try to color them. So, what this conjecture says is, you can color only using only 4 colors, so that no 2 adjacent countries will have the same color. So, you can color only with 4 colors, so that no 2 adjacent countries will have the same color. This is the 4 color conjecture. It is a very simple statement. Any 2 persons having no knowledge of mathematics can discuss about this conjecture. They can understand easily, they can also forget easily, but still it is unsolved, because it is a simple problem which is understood by any layman and it can be discussed, but no proof is given till now. But of course, some mathematicians they tried to provide a proof for this conjecture, but it was with so many limitations, where the number of countries was less than 40 and less than 50 like that. So, nobody till today nobody supplied a proof for a general case, and some time back there was a proof, but it was with some flaws, so it was rejected. So, my dear students, try this conjecture and try to prove how it can be converted into a graph. So, since it is a map, points are denoted by the countries denote points. So, points we denote them by countries on the map, and whichever countries have adjacent borders, they will be connected by a line, So, is it clear? So, now if you want to map this, you have to map the points so that no 2 adjacent points in this graph have the same color. So, that minimum number of colors is 4, that is what this conjecture says. So, you can read any book on graph theory, that certainly gives about 4 color conjecture. So, I hope in near future a proof for this conjecture will come into the light by student community. So, thank you very much for giving me this opportunity to enlighten some topics on graph theory. Thank you.